Hi, I'm Jim Heffron. These are my lessons in Calculus 1. Today we're continuing with the different methods of differentiation, and today it's implicit differentiation. So let's get started. So the point here is about functions. A function is not a formula. A function is an input-output relationship. For every input, there is one and only one output. And so what we're talking about today is how do you deal with a case where that's just not so. And the perfect example is the unit circle. So I have here a unit circle, x squared plus y squared equals 1. And I'm going to pick an x, maybe that one right there. And you see what the problem is with that x is associated not just one, but two different y's. So here, a y is not a function of x. In fact, there are some x's where there are no y's at all, but we're mostly focused on the curve. So here, y is not a function of x. Y is related to x, of course it is, but y is not a function of x. There's a problem, because when we go to take the derivative, we want to take the limit as h goes to 0 of a fraction, and the top of the fraction says f of minus f of, but there is no f. So what to do? So if we, for instance, focus on a small arc of the circle around the point x, y, here I happen to have a small arc of the circle around theta equals pi over 4 radians, then on that arc, y is a function of x. So we're just focused on a small arc of the circle, and on that arc, y is a function of x. I'm not looking at the part over here, I'm not looking at the part over here, and I'm also not looking at the part over here. On that arc only, on that arc, y is a function of x. So we're going to restrict our attention to a small arc and proceed by thinking of y as a function of x. Sometimes people write that thought down by saying it's a kind of an odd construct, isn't it? Y equals y of x. But it's the construct that people use, and so it's the one we're going to use. All right, so from the unit circle, I want dy dx. I want to figure out what is the rate of change of y as x changes. So I'm going to proceed by writing y as a function of x. I'm focused on that small arc. I'm thinking of y as a function of x. And sometimes you'll see people just say, think of y as a function of x, and then just write y. And you've seen me operating for a couple of weeks now, and I'm afraid that if I don't write y of x, that I'll flub it up. So I write y of x. Okay, so I'm thinking of y as a function of x and explicitly expressing that. Now I'll take the derivative of both sides, the derivative of the left-hand side and the derivative of the right-hand side. The derivative of the right-hand side doesn't give me any trouble at all. Of course, when x changes, 1 doesn't change at all. The derivative of the left-hand side, I know how to take the derivative of 2x. There it is, not hard. What's the story with a function of x quantity squared? Well, that's the chain rule. So the function of x quantity squared, there's the derivative of the square, there's the derivative of the function of x. So the fact that I wrote y explicitly as a function of x explains to me what's happening here. And I don't know, I like to know what's happening. So I'm explicitly writing y as a function of x. Now once we get past the derivative, I often will skip the of x part because I don't need it anymore. So I'm going to drop the y of x prompt because I've already remembered to apply the chain rule, and I'm just simply taking this formula, this here, and solving it for dy dx. So there's a variety of things that a person could do, but what I decided to do was I moved this stuff over to the other side of the equation, and then I divided by minus 2y. Here we go, divided by minus 2y, and I ended up with what I have here, minus x over y equals dy dx. For example, I focused on the pi over 4 radians point on the previous slide. So at the pi over 4 radians point, we know that x and y are both square root of 2 over 2. And so if you plug that into that minus x over y expression, you get a slope of minus 1. And indeed, it does look like a minus 1, doesn't it? Okay, so the lesson here is that we are thinking of y as a function of x, and that's to settle the problem of being a function so that the definition of derivative is correct. I'm explicitly writing y as a function of x. I like to understand what I'm doing. I'm not what I really hate in my class. Sometimes you hear it and you can't shout or jump up and down. But I really hate to hear too much of it. Is when people say, "Never mind why it is," or "I don't understand why it is," but you always do this. Never mind why. I hate that. I like a person to have some idea what's happening, and in this case, why? How come we're treating x differently than y? So I'm going to talk about that here. What's with the y of x? Thinking of y as a function of x and explicitly expressing that explains why, how come, when I differentiated, I treated y differently than x. I mean, look at here. When I took the derivative of the x part, I got an expression that looked very different than when I took the derivative of the y part. How come? And the answer is because I'm thinking of y as a function of x, not the other way around. I'm thinking of y as a function of x. So of course they come out differently. I applied the chain rule and they come out differently. Briefly, the mistake that a person can make here, and people make it, and maybe you will make it. I know I've made it. The mistake that people make here is they say, well, you have an x squared, you have a y squared, take the derivative. Derivative is 2x, derivative is 2y, and that's not right. Just not right. The dy dx is gone. Anyway, it's just not right. Okay, so I'm explicitly expressing that y is a function of x in order to understand how come I treat y differently than I treat x. It also reminds me why it is that we have trouble at some points x comma y. The formula dy dx equals minus x over y from the prior slide is undefined at y equals 0. Now you can say that's because this is a vertical tangent line, and vertical tangent line is got an undefined slope. Okay, fair enough, nothing wrong with that statement, but I can also understand it in a different way, is that when I focus on the small arc, no matter how small I make an arc around the point where y equals 0, no matter how small an arc it is, nearby x's will be associated with two y's. If I was focusing on y equals 0.1 or y equals 0.2, I could make the arc small enough so that nearby x's, that's fine. But at the place where y is 0, no matter how small an arc I make, I will not have a functional relationship. So the idea of difference quotient, f of minus f of in the numerator is just not going to happen here. Okay, high time to stop talking about the theory and to do some more examples. And we really only have a couple more because there's only so much more to see. So here, instead of a circle, I have an ellipse, and I'm interested in the point 0, 2. Now I want to read it because there's something about the wording. A point is moving on the ellipse for x squared plus 9y squared equals 36. When that point is at 0, 2, its x coordinate is decreasing by 2, and then it says units per second. So this is about time. Time is involved here. The x coordinate is a function of time. And then it says how fast is the y coordinate changing at that moment. So the y coordinate is also a function of time. The dot is moving around the circle over time. And that's exactly what it says right here. The dot is moving around the circle over time. So I think x and y are both functions of time. So in the formula, 4x squared plus 9y squared equals 36, the right way to understand that formula is to think that x is a function of time and y is a function of time. And the question says, how fast is? So the question is asking for dy dt. Okay, but with it explicitly written out now, taking the derivative of both sides, a person is going to spot that this calls for chain rule and this calls for chain rule. So I did that. I took, so 4 times, it's 2x dx dt. There's the chain rule. You can see I like to write the underbars. And when you take the derivative of the other part, you get 9 times 2y dy dt. And it all makes sense. It's 2y dy dt because it's a chain rule, because this is a function of time, namely y of t, squared. So it's a function applied to a function, and that's chain rule. So it all makes sense. And now to solve, you just plug in. Let's see. So at the point of interest, x is 0, so that explains why this is 0 right here. At the point of interest, the x coordinate is decreasing by 2 units per second, so that explains why that's a minus 2. What's the deal then with the y? Well, at the point of interest, y is 2, so 2y is 4. That's good. And dy dt, well, the question asks, what's dy dt? Of course, I have to solve for it. And when you solve, you get dy dt equals 0. And now that I think about it, I should have seen that right at the start because, whoops, touching the wrong thing on my pen. There we go. Because the x coordinate is x and y are changing with time, so the dot is moving up the curve. You see how I changed to red there? Very clever. And the dot is moving up the curve. And at this moment, we're looking at x's motion is to be decreasing at 2 units per second. At this moment, that the point is not got a vertical motion at all. It's entirely horizontal motion at the instant of this drawing. So not have a vertical motion at all means dy dt is 0. Okay, so I should have seen that right at the beginning. Anyway, the calculation got it for me. So, great. Okay, next example. It says, I got some crazy formula here. I don't know what this relationship between x and y looks like. Who the heck knows? Could be some kind of thing. Who knows? It says the point 1, 1 is on the curve. Find the line tangent. Who knows? Who knows? Okay, but we can do it because we can do the algebra. So we think of y as a function of x. There we go. Apply the apply the ddx to both sides. So there it is. I took the chain rule on the y of x to the 4th power. Here I have x times y of x, so I took the product rule. I used the over bracket just because I have a two-term expression. I'm trying to help a person keep track of what's happening. So that's the product rule. Let's see. So you write down the first, you take the derivative of the second. Sure enough, it says dy dx. Then you write down the second, and you take the derivative of the first. So I think I did that right. Derivative of x cubed is 3x squared. Derivative of minus x is minus 1. Derivative of 2 is 0. I didn't bother to write it. So it's all proceeding very routinely because I remembered to write y of x so that I would not mess it up. I would not make it be the case that I just wrote 4y cubed and stopped. But you'll notice that once I take the chain rule, I no longer bother to write y of x. It's just a question of trying to save energy, that's all. When you solve here, I happen to solve by factoring out on the left a dy dx and moving everything without a dy dx to the right-hand side over here, and then dividing through by the 4y cubed plus x, and I get an expression that's some kind of mingled combination of x's and y's. Looks kind of complicated, but if I plug in 1, 1, then I get the slope of the tangent line. There it is, slope of the tangent line. And the point, so this is the point slope form, y minus 1 and x minus 1, and that's the equation of the tangent line. Okay, so again, to me, the thing that a person can get wrong is a person can forget who's a function of who. So I write that out explicitly. And here's one to practice. And as usual, I think you should pause the video and then try the problem on your own. If you get stuck, that's fine. People get stuck. But at least you know what point it is that's giving you trouble. So I'm going to pause for a second. Okay, and I'm back. So here I wrote, it says find dy dx. So y must be a function of x. And I wrote y as a function of x. I wrote y as a function of x. I took the derivative of 2x squared, there it is. I took the derivative of y, x times y of x, that calls for a product rule. I took the derivative of y of x squared, that calls for a chain rule, there it is. And a person can lose a minus sign, of course, that's all fine, but it isn't really that hard at this point in the course. I solved for dy dx, so basically I moved all the stuff that did not have a dy dx to one side, minus 4x. Minus y, and then on the other side I had dy dx, and what was left? There was an x and a minus 2y, and divided both sides by x minus 2y. There I go. Okay, so I found the formula for dy dx. Okay, very good. So, of course, what's next is we're going to practice doing some homework. Very good.